What's up, my dudes? 6.1.4 AP Calc. This is the homework. We're going to be skipping a good amount of it. So before we even get started, we're not going to do 648. We're not going to do 650 Part A. We're not going to do 652. And we are not going to do 653. We'll look at 653 for a minute, but we're going to skip a lot of this. But even then, there's still a lot of good stuff here. So away we go. 646 during a race, Victor travels with a velocity of v of t equals 2 to the t, where t is measured in seconds. He wins the race in 6.136 seconds. Approximately how long was the race? Key question, how long? Distance. We're looking for a distance function here. So when given a velocity function and asked to go to a distance function, we are going to think about this as an area under the curve or an integral, which I have already set up for you, in fact. 2 to the t power is going to look like that. It's an exponential function where it just kind of steadily grows. And we know the race is over after 6.136 seconds. So we're really asked to evaluate this integral, the integral from 0 to 6.136 of 2 to the t power. Now you could do this with areas, but that's actually really hard to do, so we're not going to. We're going to use antiderivatives. So we got to think of the antiderivative of 2 to the t power. Well, 2 to the t is in its own derivative, so we at least know that our antiderivative will also involve 2 to the t. However, if you take the derivative of 2 to the t, what you're going to get is you're going to get the natural log of t times. So the derivative here is the natural log of 2 times 2 to the t. What we need is a way to cancel out that natural log of 2. So what we're going to do is we're going to take this and put it over the natural log of 2. And that's going to be our antiderivative. That's it. We're going to evaluate this from 6.136 to 0, which is itself very easy to do because plugging in 0 will make it 1 over natural log of 2. So we are going to need to do some work there. So for our actual calculation, it's going to be 2 to the 6.136 power over natural log of 2 minus 2 to the 0 power over the natural log of 2. And we'll let the calculator handle pretty much all of that work from here. The natural log of 2 is just a number. We're never going to know what it is. Or, well, it's never going to be anything nice. It's going to be a weird decimal. But so our first step, oh, come on, zoom feature. Okay, here we go. First fraction is 2 to the 6.132 power over the natural log of 2. Let's make sure I put a second parentheses on there. Minus another parentheses. This time, I do know 2 to the 0 power is just 1, so 1 over the natural log of 2. And that's going to give us 99 point something. Is that what the published answer says? I got the answer guide over here. I feel like it was something different. They have minus 1. Well, they have that same thing, but they have a slightly different answer. I wonder. It's not very far off. I have 99.736. The book says 100.017. We're only off by like 0.3 something. So I wonder what the difference is there. I wonder what happened. I think it's this. You can feel free to disagree with me in the comments below. Who knows? Oh, you know what it is? It's 1.6.136. That's what it is. I see it right there on my calculator now. That's what it is. Ah, there we go. Okay. See, I knew it. I was like, I probably just made like a keystroke error or something. There you go. Oh, this should be in feet. Because it was in feet per second was his velocity. Okay, let's move on into the next phase of our journey. 647, which is setting up for a concept called implicit differentiation. I have this marked as a preview question. Don't panic. Implicit differentiation is actually really simple. I know I've said that a lot this year, but let's sketch a graph of x squared plus 4 squared equals 4. For those of you not in the know, this is a circle. It's a circle whose center is 0, 0, and it has a radius of 2. There's a formula that you may or may not have ever seen at any point in your life for the formula for a circle, but that's what that is. It's a circle, and classically a circle is not a function, which is why you'll see both x and y being used in the equation. It fails the vertical line test. However, we are actually going to predict the slopes of the tangent lines at x equals 0. This is a radius of 2, by the way, before I forget. And that would happen right there and right there. We're going to have 2 of them. And the slope of those tangent lines, you know, if you've drawn this already, you probably already recognize the slope of those lines is both 0. So the slopes of the tangent lines, I would say, it's weird to say derivative, but I'm going to say m equals 0. I'm just going to write it as m. There you go. Now we're going to confirm that by differentiating, and we're going to do that to solve for y first. So let's just do some math over here to the side. X squared plus y squared equals 4. Well, that means that y squared is equal to 4 minus x squared. And here's how we usually see circles written, is the square root of 4 minus x squared. You just got to remember this, it's plus or minus. Plus and minus 4 minus x squared. We're only going to deal with the positive version of this, though, for this proof. So the derivative, dy dx, well, you're going to need a chain rule for this. Let's see. The derivative of the square root is 1 over 2 times the square root. We have to leave the original inside intact, and then multiply by the derivative of the inside, which in this case is just negative 2x, like that. So our finalized derivative, let's write it as negative 2, actually the 2's cancel out. So it would be negative x over the square root of 4 minus x squared. Now, we're going to evaluate this when x equals 0, and that's really easy to do because the top of the fraction is 0, and so the whole thing is 0, which we kind of knew already from looking at the graph. You can do that exact same exercise with the negative square root, and you'll just get a positive x on top. It's also 0. So we have a much better way of handling this in the future. By the way, we will not be using this process. This is a preview question, really intending to show you what you don't need to do. Okay, let's move on. We're not dealing with 648 because we've already done one acceleration velocity problem in this lesson. We don't need to do more. Let's do some derivatives. None of these are going to be quick. They all are going to require multiple steps, so let's map out our thinking. Let's do A right here in this space. This is going to require a product rule, because the products are 2z squared and the secant of z to the third minus 2. So let's map it out. U is 2z squared. V is the secant of z to the third minus 2. And the secant is going to require a chain rule. Du is going to be 4z. That's pretty simple. And dv, yikes. The derivative of secant is itself times the tangent. So it's going to be the secant of z to the third minus 2 times the tangent of z to the third minus 2, and you have to multiply that times 3z squared, like that. So let's see. I'm going to rewrite that as the 3z squared in front, secant of z to the third minus 2, tangent of z to the third minus 2. Wow, that is not fun to deal with at all, but we're going to leave this in its most bare bones form and then walk away. So for question A, this is my answer, I guess. ddz equals. Let's see, the original first times the derivative of the second. The only thing that's going to happen here when these two guys combine is that the 2z squared and the 3z squared will actually multiply together to make 6z to the fourth. But then everything else just tags along. Secant, z to the third minus 2, tangent, z to the third minus 2. Don't get hung up on all this writing. Those are all just 3 things being multiplied together. And then the next chunk is plus 4z times the secant of z to the third minus 2. And that's it. I would not do anything else in this problem at all. Just checking to see my answer is correct. Yeah, okay. They factored out an answer in theirs, but who cares? Let's talk about B for a moment. Sine of tangent squared of 3t minus 5. Yikes. This is going to be a triple chain rule problem, or maybe even more. It's going to be a quadruple chain rule problem. Here is the outside function is the sine. The next function is is something squared, because the tangent is being squared. But the thing being squared here is the tangent, and the thing inside of the tangent is 3x minus 5. So there are actually 4 parts to this. Oh, you know my window's all messed up. Let's keep writing on this. So we have to be really careful here in part B. I'm going to write the original problem up here. ddt of the sine of the tangent squared of 3x minus 5 is the original problem there. Okay, so we got to be careful. Let's handle this. Understand this is a challenge problem that is not indicative of what you'll see on your AP test. Just kind of extra see how much resistance you can put in this front of this thing. Okay, the derivative of the sine is the cosine. So we'll start there. Cosine, leave everything else in the inside exactly as it was. There is the first part, done. Next, we got to multiply by the derivative of x squared, which is going to be times 2 times the tangent of 3x minus 5. And then technically that's the first power, but we use the power rule, so that's done. Now we're going to multiply by the derivative of the tangent, which is the secant squared of the 3x minus 5. So that's done. And then we finally multiply by the derivative of 3x minus 5, which is 3. So as far as cleaning this thing up, the only thing I see that really combines in any meaningful way is the sine, as 2 times 3 is 6. So the cleanest way I could write this is 6 times the cosine of tangent squared of 3x minus 5 times the tangent of 3x minus 5. This problem sucks. Times the secant squared of 3x minus 5. There's probably some other ridiculous BS simplification we can do there, but I already hate this problem. Question C. Derivative of x times 2x, 2 to the x cosine x. I don't remember what it was again. X times 2 to the x. One more time, I'm going to look at it. Cosine of x. Okay. This is a triple product rule. The way I think we should handle this, when you're dealing with a product rule inside of a product rule, we'll talk about this in class a little bit today. When dealing with a situation like this, I would just pick the first two and just work that out separately. So if we talk about x, u is x, and v is 2 to the x, du is 1, and dv is natural log of 2 times 2 to the x. The first chunk of this, I'm going to kind of use colors to separate this out. And I'm just doing the product rule, and then I'm going to leave the cosine x off to the top. Hopefully there's enough room in that little red box I just made. So I'm going to have x natural log of 2 times 2 to the x plus 2 to the x. Oh, not enough room. Not more room than I needed. Cool. That's the first part. We just handled the derivative of the first two things. And now we're going to treat this like another product rule problem. The first thing is x natural log of 2 times 2 to the x plus 2 to the x. That's not going to be fun. Wow. Wow. Would it have been easier? Man. Because that's going to itself require the product rule, which seems to me to be excessive. Well, so you keep pressing forward, I guess. And so v equals cosine of x. du, yikes. Wow, is that also a triple or a double? No. Sorry, I'm kind of flabbergasted here. Well, if I do this, this is going to require itself another product rule. The natural log of 2 is just a constant, so it can hang out in front. But it's the natural log, I guess the original first part would be natural log of 2 times x. So I'm just going to say x natural log of 2 times the derivative of the second, which would be natural log of 2 times 2 to the x, plus the derivative of the first, which would be natural log of 2, because the x just becomes 1, times 2 to the x. And that is plus the natural log of 2 times 2 to the x. That's the derivative of the 2 to the x part there. I think that's right. That's a lot of natural log of 2's. And the derivative of v is the negative sine of x. Wow. Did I miss something in this problem? Is there because I'm looking at the published answer, and it's much simpler. But I don't think they're right. 2x. Yeah, I don't think the published answer is correct, though, because they've got a bunch of different terms here that I'm not seeing. So I'm just going to go forward with it and clean it up and do the best I can. So the final derivative here, hilarious. U times dv, yikes. I'm just going to leave it as negative sine of x times x natural log of 2 times 2 to the x plus 2 to the x. That's the first chunk. Plus the cosine of x times all that other crap. X natural log of 2 times natural log of 2 times 2 to the x plus natural log of 2 times 2 to the x plus natural log of 2 times 2 to the x. Oh, weird. I guess there are a couple of different... I'm sure I could do a lot of clever factoring to make things easier, but that's it. I already hate this problem, so... Yikes. You know, looking at these, they're ridiculous. So I'm going to put a star next to them. Hey, congratulations, bonus time if you got them right. Let's talk about 650. Let's move on with our lives. Write the first and second derivatives of each function, and then use the derivatives to test for the maxima and minima. You know, I've circled B, and I... You know what? I circled B, but I changed my mind. I'm looking at the answer for B, and I do not want to do a second derivative of that at all, and I don't think it would be a very fun or useful problem to solve. I would much rather look at question A, which I think is easier to look at. This is a really common AP Calc question, too. I've seen this on a lot of different tests. So as far as the derivatives go, they're actually pretty easy to get. The first derivative is a product rule, but it's a product rule involving e to the x, which is usually really easy to clean up. So the first derivative, let's see, it's the original first thing, 2x, times the derivative of the second, which is e to the x, plus the original second thing, which is also e to the x, times the derivative, which is 2. Now, that seems pretty simple. In fact, actually, I think it'd be a best if we factored out 2 times e to the x and left x plus 1 in parentheses. That would be, I think, the best way to write that. Because for the second derivative, I'm going to leave that alone. Actually, maybe we'll work on this over here off to the side. Y prime is equal to 2e to the x times x plus 1. I'm just going to check that against the answer guide. Yes, I like that. Let's look at the second derivative for a moment. And I like writing it the way we have written it because now you can see it's going to be another product rule. It's going to be the original first, 2e to the x, times the derivative of the second, which is 1, plus the derivative of the first, which is just 2e to the x, times the original first, which is x plus 1. And that is not so terrible to deal with. In fact, you can once again factor out 2e to the x and have it be 1 plus x plus 1 or x plus 2. I like that quite a bit. That's a nice, easy one to deal with. I'm just confirming that is correct. Nope. Oh, yep, got it. I like it. Pretty good. Cool. Okay, I like that a lot. Now, the next part of the challenge is to use these derivatives to test for maxima and minima in the given interval, and remember to check the endpoints. Now, we don't really need to worry about checking the endpoints in the problem that we're doing because there are no endpoints when you're in negative infinity to infinity. So we are going to find what the critical values are, and we are going to test them to see which one is the biggest. And since there are no endpoints, we don't need to test those. So the first thing we need to do is take our first derivative and set it equal to 0. The nice thing is, because we factored it, it's already a multiplication problem. So what's nice about a multiplication problem that equals 0 is that you really just got to think about what makes the inside of it 0. What makes each chunk 0. So negative 1 is the first critical value. And I don't believe that 2e to the x has a spot that can make it 0. Can 2 times e to the x equal 0? Let me think about this for a minute. What that would mean is if I divided by 2 on both sides, I would get a spot where, let's see. Yeah, I think that's the only one, because if you divide by 2, you get e to the x equals 0, and this never happens. You can't raise e to a power, or sorry, you can't raise any base to a power and get 0, so that's not going to happen. So the only spot we got to check is negative 1. And so is it a maximum or is it a minimum? Well, what we could do is we could plug negative 1 into our second derivative and see what we get. What is y prime when x is equal to negative 1? Because if it's negative or positive, that'll tell us the concavity of the function. This will be 2 times e to the negative first power times 1, negative 1 plus 2. This is 2 over e, which is very positive. And because it's positive, what I know is that this is concave up. concave up. So what that means is that this over here has to be a minimum at that point because it's concave up on that range. So that has to be a minimum. And I know it's both a local and a global minimum since it's the only minimum there is. And its coordinates are -1, and we have to go all the way back to the original function to figure out what the other y coordinate is. It's y equals 2x e to the x when x is equal to -1. So this is equal to 2 times -1 times e to the negative first power, which is -2 over e, like that. And so I'm just going to put that as the y coordinate. And this is the local and global minimum of that graph. We could take a look at the graph right now and confirm that, but that appears to be the case there. In addition to checking for the concavity, what we could have done is we could have plugged in values before and after -1 back here in the first derivative function, and that would tell us if it went from decreasing to increasing or increasing to decreasing. That would work too. Okay, let's move on. 651 we are going to do because it's an easy question. Midpoint rectangles have their height defined at the midpoint for the interval, and so here's the function 1 over 2x plus cosine of x. Graphed it right, and we have actually done a problem like this way back in like chapter 1 or 2. We found the midpoint values, f of 1.5, f of 2.5, and f of 3.5 right there. So we're going to approximate the area under the curve using midpoint rectangles. So all we're going to do is use that information. We know that they all have a width of 1, which is nice. So the sum, in this case, is just going to be 0.821 plus 0.449 plus 0.814. Normally we would multiply these all by something, but since they're all being multiplied by 1, we just need to add them together. Really quickly going to do that. 814. We got 2.084. Then that's an approximation because it's midpoint rectangles. And, you know, we've talked about left endpoint rectangles, right endpoint rectangles. This is right in the middle, which usually requires a lot more work because you got to plug in the midpoints, but you figure it out. Now what we're going to do is we're going to calculate the exact area and compare it with our approximation. And that's actually even easier to do because all we want to do here is the integral from 1 to 4 of the function 1/2 x plus cosine of x and times dx. Because the idea here is with the integral notation, what we're doing is we're slicing that up. What dx says, we're slicing up this into an infinitely many rectangles, and we are finding the area of them over the range from 1 to 4 and adding them all together. The calculator can do this for us. In the F2 menu, you can find fn int right there, 1 to 4. Whoops. Now is a good time to check to make sure your calculator is in fact in radians because we have a cosine in this problem. Plus cosine of x dx. And that is that. I didn't mean to graph that. 2.151 is the answer the calculator spits out, which you can tell is, it's a little bit more than what we had before. It's, they're about the same, but the exact answer obviously is better. I don't know what kind of lunatic wrote a problem like 652 or expects us to do a problem like 652. Honestly, you could multiply the entire problem by x squared, by x squared, and it would actually cancel out pretty nicely, but we don't care about that. We have talked about the integrals of exponential functions a little bit here. 53 is a cool problem. I really want you to see it, but in the interest of time and just like looking at things, I mean, you could just use L'Hopital's rule for these things because it is 0 over 0. I don't know. These limits are not very important, and they are not representative of what you'll see on your AP Calc test anyway. So 654 is the next thing. We're going to evaluate these integrals using whatever strategies we have ahead of us. So let's get into it. Last problem of this video. The first one here is, well, we have to evaluate use the natural log of 3 times 3 to the x. Now, in order to do this, we should think about that math notes box up above. I know that the antiderivative of 3 to the x is, actually, that'll do it, honestly. Because the derivative of 3 to the x is the natural log of 3 times 3 to the x. So this is just, I suppose, recognizing that you understand what the derivative looks like before and after. I guess plus c. Since it's an indefinite integral, it needs to have a plus c on it. So that's that. Honestly, that one's done. Question B, let's see. We are evaluating this integral. You can do this one by hand pretty well, so let's do that. Let's leave 2 pi out of it for now, and let's simplify things a little bit to make this problem easier for us. Let's go ahead and distribute that x. We'll have 2x squared plus 5x times dx. We'll leave 2 pi, again, off to the side. So the reverse power rule will make this 2x to the third over 3 and plus 5x squared over 2. It's a pretty handy way to handle that. And we need to evaluate this from 2 to 0, which is actually really easy to do because plugging in 0 won't do anything. So all we really got to do is plug in 2. So again, let's leave 2 pi off to the side. Plugging in 2 gives us 2 times 8. 2 to the third power is 8 over 3. Plus 5 times 2 squared is 4, so that's 20 over 2. And I will put a minus 0 at the end of this thing just to indicate that, if we plug in 0, we get 0. So working one more step off to the side, we're going to have 2 pi hanging out in front. We have to think about what 16 over 3 plus 10 is. I'm going to rewrite 10 as 30 over 3. And that makes it pretty easy. In this case, you're going to have 2 pi times, let's see, that's 46. And 2 times 46 is 92 pi over 3. Does 92 divide by 3? It doesn't. So I'm going to leave it just like that. 92 pi over 3. I like that answer. Okay. Let's move on to question C. We got 4 times e to the natural log of x. Again, what you should recognize here is e to the natural log of x. That cancels out. So this is actually just the integral of 4x dx, which is actually really easy to do. It's got to be 4 times x squared over 2, which you can simplify to just be 2x squared. And don't forget plus c when you're all done. 2x squared plus c there. And then question D, this one, I don't know if we have a way of doing this. Let's see. Oh, no, we can. We can do this. This is going to be, let's rewrite it first of all as 2m times 2 squared dm. Because we're kind of using that exponent rule, but kind of backwards. In this case, if you added the exponents together, you could combine this into 1. But here, we're actually kind of thinking about it as a multiplier. In fact, this actually simplifies to 4 times 2 to the m power. And you can just kick that 4 right in front of the integral because it's a constant. And so this actually becomes pretty simple. I'm writing all over the place. This is 4 times 2 to the m over the natural log of 2. Which is the way you handle an antiderivative when it comes to natural logs like that. So there you go. Oh, don't forget plus c. I like that answer. Okay. Pretty cool. I'll post this video as soon as I can get it finalized, and you guys will have it for your homework. And I am going to be working on a instructional video for you tomorrow because I'm not going to be here, and you guys are going to look at 6.2.1 for implicit differentiation for the first time tomorrow. So I'll make a video for that for you guys to watch during class. So I'll see you in the next video. You guys are awesome, and you're great. Keep it up.